Let us now discuss on how to size PV modules for any given applications. There are two classes of applications. One set of applications does not require energy storage. So how do we size the PV modules that doesn't need batteries for energy buffering? The other class of PV applications require energy storage, require batteries. So how do we size PV modules for those applications which require batteries? We will see both these cases and see how we go about sizing PV panels. Let us list down some applications. One of the most common one is PV power being pumped into the grid. This is an important application gaining in popularity very much. You would have seen a lot of rooftop PV solar cells being mounted on the top of the buildings, and they are integrated with the inverters which are connected to the grid to pump AC power into the grid. These applications don't need batteries in general. Another set of applications which don't need batteries are the water pumping applications. One of the more common one is the underground sump where water is stored and that is lifted up to the overhead tanks. This and also the pumping for irrigating lands, vast expanses of lands. This also comes into the category where batteries are generally not needed. Another set is cooling applications like refrigeration, Peltier cooling, AC. You can make use of converting the solar power into the thermal effects without the need for batteries in general. And so also the heating applications. There are some heating applications where you do not have to use batteries. Let us consider this typical application of PV power being pumped into the grid. This is a very popular application, and let us take that as an example to consider how we go about sizing the PV panels. Now grid, let me represent the grid by these two lines, single phase grid, but it could as well be a three-phase grid. And from this grid we draw power, and also we can put power into it. So the grid is acting as a buffer. So to these grid lines we will interface loads which are within a building, and there are electrical loads inside and they need power, and then we draw the power from the grid. So in this fashion we connect the loads which are inside to the grid, draw the power from the grid, we meter it, and then operate the appliances. Now let us say on the rooftop of the building we have solar panel, and it is receiving and capturing the solar energy. So this solar energy gets converted to electrical, and let's say we meter it and then put it into the grid in an appropriate manner by using grid connected inverters. So this is the scenario. So let us take this scenario as an example and see how we go about designing this photovoltaic panels. So that will give you an insight and understanding on what we need to do. The amount of energy that you put into the grid, that is the solar energy captured from the PV panels and what we put into the grid, we will name it as WHPV, watt hour PV. So watt hours is the unit of energy, and that's what we will be using. And watt hour load, let me call this as watt hour load, is the energy that will be consumed by the appliances within this. So If the PV power was not there, we would be only consuming the watt-hour load amount of energy on a daily basis or monthly basis and paying for that depending upon what is metered. Now that we are putting back the energy, now let us say we have a requirement that we need to have a net balance, that is a zero net energy that we need to incorporate into this design. Most of the states, most of the places, you will have a tariff for watt hours that we are drawing from the line, and the tariff for the watt hour from the solar energy that we are putting into the grid is different, generally higher. So therefore there is an advantage in trying to put the green energy into the grid. So now let us say that this watt hour load has a tariff which is C load. So it has a cost of C load per watt hour. And let us say the solar energy that you put into the grid has a value CPV, rupees CPV per watt hour. How do we calculate the net cost? So the net cost is given by watt hour load into the cost C load, the tariff C load, minus the watt hour that we are putting into the grid into CPV, the photovoltaic tariff. Now this minus this will be the net cost. So our goal, our interest is to have the net cost as 0. So for 0 net cost, we have watt hour PV required, watt hour load into C load by CPV, because net cost is 0. We can make watt hour PV is equal to watt hour load if we are interested in having a 0 net energy, in which case 0 net energy, in which case C load is equal to CPV. That is, the tariff of load and tariff of PV is same, no subsidies involved. So let us take this requirement that we would like to design the PV panels to meet this watt hour requirement, watt hour PV, which is the same as watt hour load, such that the net energy is 0 in and out of the building. Generally, the load is metered and billed on a monthly basis, and it is expressed as units per month, and it is synonymous with kilowatt hour per month. So this is the units for which it is billed and the tariffs are given. So for our purpose, watt hour load is a daily requirement. So we will take the kilowatt hour per month requirement by 30 and expressed as kilowatt hours per day, and watt hour PV is set equal to watt hour load. It may be good to take the kilowatt hour per month reading of many months, maybe every month of the year, and take the average of that and then use that for calculating watt hour load. So it could be the mean kilowatt hour per month by 30 to give a much more consistent value of the load requirement, so that the PV can address that load. A worst case design would be consider the kilowatt hour per month billed reading for the entire year, and take the highest value of kilowatt hour per month. So that would be the max requirement of energy for this building. And watt hour load can be the max kilowatt hour per month by 30, which will give you the kilowatt hour per day, the maximum that the PV has to supply in order to maintain net zero energy balance. So one can design the watt hour PV requirement either way, either taking the worst case value, the max value of kilowatt hour per month, or take the average or the mean value depending upon what your constraints are in terms of the application. Next, we need to determine the amount of daily energy that is incident on a flat plate tilted at an angle beta with atmospheric effects, and this we know how to do. So determine HAT versus N, the day number. So you will probably get a curve like this. See, this is the curve which goes from Jan 1st onwards to December 31st. N is equal to 365. So somewhere, say, let us say we have a minimum. Now this would be the worst case incident energy available on the flat plate collector, tilted flat plate collector with atmospheric effects on any day in the year. And that is what we need to find out and use that for sizing the PV panel. So find out this particular value, which is in kilowatt hours per meter square per day, HAT min. We can find out HAT by executing the script files that we discussed earlier. So this text file is hat_estimate.m, est.m. This estimates the HAT value for a given latitude. So I have chosen Bangalore as the latitude. You are familiar with the contents of this file. We have written this earlier and described this earlier, discussed it. So now let us execute that in Octave, HAT estimate. So you will get a output figure like this. So the blue line is H0 versus the day number. So this is day 1, January 1st, and day 365 on December 31st. The green line is HAT. This is the incident solar energy falling on a tilted flat plate collector with atmospheric effects. So the units are kilowatt hour per meter square per day. Now observe here, for Bangalore, somewhere here is the minimum. So if you take this point, this will be around 195. If I zoom to this place, you will see that at around 195 day number, you have the minimum value of HAT, which is around 4.6, slightly less than 4.6, 4.55 or so. You can find out the minimum value of HAT by typing min HAT array, would give you 4.5866 kilowatt hour per meter square per day, and this is at that day number 195 or 196. Now let us try to find out the day number. So the day number basically is the index of the HAT array. Let me set Q is equal to HAT less than or equal to min HAT, which means all the elements will become 0 except the element corresponding to the minimum HAT value. Then use find Q. It will find the non-zero element of Q, which is at index 196. So HAT 196 should contain the minimum value 4.5866, and 196 will correspond to July. N is equal to 196 will fall somewhere in July 16th or so. So you can type in the calendar and type in here, let us say month 07. So somewhere here July 16th would correspond to 196, or you could use the date num command like this. So the date num command gives the number from the Unix timestamp, how many number of days. So this is 16th July 27 minus date number of 1st January 2017. So from 1 you will get the date number. So this is 196, which will be 16th July. So basically on around 16th July you have the minimum HAT value, which is 4.58 kilowatt hour per meter square per day. Now that is the crucial and the important value that you have to take away from this, and you have to design your PV panel to deliver the full load requirement even during this low insolation, least insolation day. Then any other day in the year is covered. Let us understand the implication of finding HAT minimum and using it in our calculations. So let me draw this X and Y coordinate systems where X represents T, time in hours. This is time in hours of the day, 0 to 24 hours. And the y-axis is L, the insolation in kilowatt per meter square. And let me indicate the salient times, 6 a.m. and 6 p.m. And let me draw the approximate insolation curve, which looks something like this. The area under this, the integral of this, is the energy, and that energy is HAT minimum. So every day of the year you will have a waveform of the insolation something like this, and the area under that would give you HAT. And we have looked at the HAT of all the days of the year, the entire year, and found that on a particular day in the year we have minimum energy incident on the tilted surface with atmospheric effects. So that is this HAT minimum, and for Bangalore we found that this value is around 4.58 kilowatt hours per meter square per day. Now this picture of the insolation versus time is equivalent to, can be equivalently written in this fashion. I am writing another T versus insolation L graph. Now on this I am going to mark the line indicating the standard insolation L standard, which is 1 kilowatt per meter square. This is 1 kilowatt per meter square. Now can I map this area into a rectangular area having a maximum value of insolation of L standard, which is 1 kilowatt per meter square. So let me mark the line corresponding to noon. On either side of noon I will draw these lines, and you have this rectangle, and the width of this rectangle is equal to this value, numerically equal to 4.58, let us say, for this specific example. So I will keep this width at 4.58 hours. At any other value of HAT, it will be HAT hours, numerical value of HAT hours. So what is this area? Now this area will be height 1 into the width 4.58. So this area is also exactly equal to this value. So this would give you an equivalent area which corresponds to HAT minimum. The only difference here is that this is a rectangular profile, and it says that if 1 kilowatt per meter square standard insolation is applied, then only for 4.5 hours you can have incident radiation. So let us draw the symbol of the solar panel, and it has the output terminals as indicated. Now on the input side, sunlight, solar light is falling on the panel, and that is at 1 kilowatt per meter square insolation. Now the panel itself is having an area, and let's say a meter square. Now 1 kilowatt per meter square into a meter square, 1 kilowatt into 1 kilowatt per meter square into a would be the amount of power input that will be falling onto the panel, and at the output you will get efficiency times efficiency of this panel into 1 kilowatt per meter square insolation into a meter square panel area into this many hours, 4.58 hours, will give you the kilowatt hours out of the panel per day. Every day you will get this much amount of energy out of the panel. So in a more generic terms, let us say, now this is P in. 1 kilowatt per meter square into the area will give you the power input, and this is numerically equal to HAT minimum. So this is numerically equal to HAT minimum. So generalizing, we will say efficiency into efficiency, as this is 1, then into A into HAT minimum is equal to watt hour PV. What should this be equal to? The output of the photovoltaic panel set should be able to supply the load requirement, which we had set it as WHPV, coming from the application side. So therefore the area of the panel that we should actually buy and install is WHPV, the load requirement, by the efficiency of the panel into HAT minimum. Now this would be the design equation for sizing the photovoltaic panels for an application without battery, where WHPV is the application load requirement. This is a picture of solar panels mounted and installed on the roof of my department building. Now these are solar panels, and the A that we calculated corresponds to the area of the solar panels. However, the real estate is required is slightly more than the calculated area A, Observe that you need some in between spaces where you need to mount, work on the panels, you need to clean the panels, you need a pathway, an aisle here, so that you need to have maintenance people move around, and also for cleaning people to clean and maintain the panels. So they, not only that, you may want to space out the sets of panels so that the shadow, you see, observe the shadow of this panel falling here doesn't fall too much onto the neighboring panels, and thereby lose out on the available output power. So therefore some amount of spacing is needed, and this is dependent on the place where the panels are installed. So in general, the real estate needed will be more than the calculated area A, electrically calculated area for the panels. So the A that is calculated is called the intrinsic area. However, the practical real estate needed will be 30% more than the calculated. So approximately you can set aside extra 30% for all these spaces for maintenance and cleaning operations. So this calculated area is called the intrinsic area in meter square. However, we need to evaluate what is the actual real estate that you need. So we will call area estate that is required will be area intrinsic, that is calculated like this, and plus you have to add the area needed for maintenance purposes, the service area. Set aside approximately 30% of area intrinsic for maintenance purposes, and therefore you will have the area estate equal to 1.3 times area intrinsic. So this would be our area needed for a particular application of particular given watt hour requirement.